Good morning, students. So, yesterday we have discussed two applications of Gauss law. The first one, the electric field due to an infinite long line charge. Okay, then the electric field due to a thin charge sheet. Okay, now here before starting the class, kindly pay attention. The comments are open, so you will write your name. Okay, when you watch the video, you will write your name. Then I'll take the attendance from that. Okay, so 2 days will be given. Like yesterday, from yesterday you will start. Yesterday was 19th, so 19, 20th. For 2 days I'll watch, and then on 21st I'll give the attendance of 19. The same way for every day. So every video you watch, especially as I'm the class teacher, so I'm talking about the physics video. So every video you watch, then you will write your name. Okay, the comments are open. Write your name so that I'll mark your attendance from there. Is that clear? So write your name in the comments. Okay, now let's start. Two applications we have done. The first one, the electric field due to infinite long line charge. Okay, and we found out the expression of the electric field due to infinite long line charge, which is equal to lambda upon 2 pi epsilon naught into r. Okay, whereas due to the thin sheet, electric field is equal to sigma upon 2 epsilon naught. Okay, here you can see that the electric field is independent of r. Okay, independent of the distance. Okay, at whatever point, this was the thin sheet. Okay, suppose we are finding out at point P, which is at r distance, or if we find out at this point, Q point, then also it will be sigma upon 2 pi, sigma upon 2 epsilon naught. So it is independent of r. Okay, now here we'll find out the electric field due to two thin parallel charge sheets. So write the heading. Electric field due to two parallel charge sheets. Okay, now there are two charge sheets which are parallel to each other. Let on both the sheets positive charges uniformly distributed. Okay, now here I am now drawing the sheet. The sheet is perpendicular to the plane of the board. So these are the two sheets on which let positive charges uniformly distributed. So the surface charge density of the first sheet, let it be sigma, and the surface charge density of the second sheet, let it be sigma 2. Sigma 1 and sigma 2 are the charge densities of these two sheets. Okay, now we know that the electric field due to a single sheet is sigma upon 2 epsilon naught. So the electric field due to the first sheet is sigma 1 upon 2 epsilon naught, and the electric field due to the second sheet is equal to sigma 2 upon 2 epsilon naught. Let us consider here that sigma 1 is greater than sigma 2. Okay, just consider that let sigma 1 is greater than sigma 2. Okay, so now here we'll find out the electric field in different regions. This is the first region, which is to the left of the first sheet. The second region is between the two sheets, and the third region is to the right of the second sheet. So we'll find out the electric field due to these two sheets in these different regions. Okay, now in the first region, the electric field due to the first sheet. Okay, first we'll draw the direction. Magnitude is sigma 1 upon 2 epsilon naught, which we have derived yesterday. What will be the direction of the electric field? E1, away from the positive charge. Okay, as we know that the electric lines of forces are from positive to the negative charge. So it will be away from the positive charge and towards the negative charge. Okay, due to the second sheet, again this is having a positive charge. So the electric field due to the second sheet is also pointing towards left in the first region. Okay, now let's find out the electric field in the first region. Okay, this is the first region. Okay, as we see that the electric fields are pointing in the same direction. So electric field will be equal to E1 plus E2. That is 1 upon 2 epsilon naught sigma 1 plus sigma 2. Okay, also you have to write the direction. What will be the direction? Towards left, as both the electric fields are pointing towards left. So this electric field in the first region will be towards left. Now in the second region, okay, due to the first sheet, the electric field is pointing away from the positive charge. Due to the second sheet, again the electric field is pointing away from the positive charge of the second sheet. Now here we see that in the second region, the electric fields are pointing in opposite directions. So the net electric field in the second region will be equal to the difference of these two. So here we have considered that sigma 1 is greater than sigma 2. So the net electric field will be equal to E1 minus E2. That is 1 upon 2 epsilon naught sigma 1 minus sigma 2. Now what will be the direction? As E1 is greater than E2. So here in this case, it will be pointing towards right. Okay, if E2 is greater than E1, because here we have considered that sigma 1 is greater than sigma 2. But if sigma 2 is greater than sigma 1, then E2 will be greater than E1 and then it will be pointing towards left. Okay, but in this case, it is pointing towards y because E1 is greater than E2. So it will be pointing towards right. Okay, it's very necessary to write the direction. Now in the third region, the electric field due to the first sheet pointing away from the first sheet, due to the second sheet also pointing away. So the net electric field in the third region is equal to, again both are pointing in the same direction, so it is equal to E1 plus E2. That is 1 upon 2 epsilon naught sigma 1 plus sigma 2. Okay, now what will be the direction? As both are pointing towards right. Okay, both the electric fields are pointing towards right. So the direction of the electric field will be towards right. It will be towards right. Okay, so this way we can find out the electric field due to two parallel sheets having surface charge densities sigma 1 and sigma 2 in different regions. Okay, towards the left of the first sheet, that is the first region, between the two sheets, second region, and to the right of the third sheet, which is the third region. Okay, so note it down. So here we have found out the electric field due to two parallel sheets. Okay, so these are the two parallel sheets having different surface charge densities. Okay, one is having sigma 1, the other is having sigma 2. So here we have considered let sigma 1 is greater than sigma 2. Then we divide in three regions, first, second and the third region. We find out the electric field in the first region. As electric field is a vector quantity, you will write its magnitude as well as know its direction. Okay, direction of the electric field away from the positive charge. So first sheet is having the positive charge, the electric field is pointing away. The same way the second sheet is also having positive charge, the electric field is pointing away. In the second region, that is between the two sheets, the electric fields are pointing in the opposite direction. So the net electric field will be the difference of these two. Okay, and also you have to write the direction as E1 is greater than E2. So the net electric field in the second region will be along E1, that is towards right. Whereas in the third region, both the electric fields are pointing in the same direction. So the net electric field in the third region is sum of these two, E1 plus E2. Okay, and it will be pointing towards right. Okay, now let us consider one case. If both are having equal and opposite surface charge density. So here only write down. Let us consider a case. Okay, we will consider that both are having equal and opposite surface charge densities. So write down. Both sheets having equal and opposite surface charge density. What does it mean? Opposite surface charge densities. That is sigma 1 is equal to sigma and sigma 2 is also equal to sigma, but opposite means if sigma 1 is plus sigma, sigma 2 will be minus sigma. Is that clear? Equal and opposite surface charge density. Now again we'll find out the electric field in the three different regions. So here this is plus sigma, this is minus sigma. This is the first region. Second region is in between the sheets and the third region is to the right of the second sheet. Okay, now what will be the electric field in the first region? That is, this is having plus sigma means positive charge uniformly distributed, minus sigma means negative charge uniformly distributed on the sheet. Okay, what will be the electric field? Here you can find out from the formula which we have derived, which was 1 upon 2 epsilon. In the first region, it was 1 upon 2 epsilon naught sigma 1 plus sigma 2. So what will be the electric field in the first region? It will be 0, 1 upon 2 epsilon naught. The electric field in the first region was 1 upon 2 epsilon naught sigma 1 plus sigma 2. Okay, as sigma 1 and sigma 2 both are equal and opposite. So sigma minus sigma, it becomes 0. Okay, the same way in the third region. First, let's find out in the third region. In the third region also, it was 1 upon 2 epsilon naught sigma 1 plus sigma 2. So sigma minus sigma, here also it becomes 0. So the electric field to the left of the first sheet and to the right of the second sheet is 0. No electric field exists outside the sheets. Now let's find out in between the two sheets. Okay, that is in the second region. Electric field due to either you can find out from the formula which we have derived. That was 1 upon 2 epsilon naught sigma 1 minus sigma 2. So how much it would be? Sigma 1 is plus sigma, sigma 2 is minus sigma. So sigma plus sigma, that is 2 sigma upon 2 epsilon naught. Or we will find out by taking the directions. Due to the positive charge, the electric field is pointing away. This is the direction of the electric field due to the first sheet. Due to the negative charge, again it is pointing towards the negative sheet. So the net electric field in the second region is equal to 1 upon 2 epsilon naught sigma 1 plus sigma 2 sigma 1 sigma 2 both are equal to sigma. So 2 sigma upon 2 epsilon naught, so it is equal to sigma upon epsilon naught. Okay, so the electric field only exists between the two sheets. If the surface charge densities are equal and opposite, then the electric field exists only between the two sheets, which is equal to sigma upon epsilon. And what will be the direction? Towards right. Here it is 0, so no need to mention the direction. So here we have considered a case when the electric fields are, we have found out the electric fields in these three regions when both the sheets are having equal and opposite surface charge density. So write down this case also. The two sheets having equal and opposite surface charge densities. That is sigma 1 is plus sigma and sigma 2 is minus sigma. Okay, so the electric field in the first and the third region, magnitude was the same, 1 upon 2 epsilon naught sigma 1 plus sigma 2. Okay, only the direction was towards the left of the first sheet, that is in the first region, it was pointing towards left. In the third region, it was pointing towards right. Okay, but here, sigma minus sigma, it becomes 0. So the electric field in the first and the third region becomes 0. But the electric field exists only between the two sheets, which is equal to sigma upon epsilon naught, and also write the direction. What is the direction? Towards right. The direction is towards right. Okay, now one more application is left. We'll find out the electric field due to a charged spherical shell. Okay, now here we have to find out the electric field due to a charged spherical shell. Okay, note it down. Okay, here one question I'll give you, which you will solve it, and tomorrow we are going to discuss. It has come in CBSE board. The question is, I'm only drawing the figure. Two sheets, one having plus 3 sigma surface charge density and the other having minus 2 sigma surface charge density. Okay, now here you have to find out the electric field in region 1, electric field between the two sheets, that is in region 2, and the electric field to the right of the second sheet, that is in region 3. Okay, so this is the homework. You will try it. Tomorrow we are going to discuss. Okay, the same way you will do it. Due to this sheet, the electric field is 3 sigma upon 2 epsilon naught. The electric field due to the second sheet is 2 sigma upon 2 epsilon naught. Okay, so here you will not write it as minus. Okay, here we are going to draw the direction due to this plus sigma or minus sigma, that is plus charge or the minus charge. So automatically the direction will give this negative sign. So any vector quantity, if it is positive, negative, here you don't write it as minus 2 sigma because we are going to draw the direction. We will find out the electric field in all the 3 regions. Okay, and also the direction. Okay, direction either you can write down as towards right or towards left or towards the first sheet, towards the second sheet, whichever you find it convenient, you can write down. Okay, it's better to write towards right, towards left, that is good. So this is the homework. Today you will try it. It has come in CBSE. Okay, now the last application of Gauss law is electric field due to a charged spherical shell. So write the next application, the third application, electric field due to charged spherical shell. Okay, the same way we'll do it. We'll draw the charged spherical shell. Okay, and wherever we have to find out, we'll draw a Gaussian surface and we'll enclose the charge. Okay, this is a charged spherical shell, that is positive charge uniformly distributed on this spherical shell. Okay, which charge density will consider here? Surface charge density. Why? Because the charge is uniformly distributed on the surface. It's like a hollow sphere, okay, on which this positive charge is uniformly distributed. Let the radius of this shell is capital R. Okay, the radius of the spherical shell is capital R, and we have to find out the electric field at a point P, which is outside the shell. Okay, point P is lying outside the shell. So here we draw a Gaussian surface which will enclose this charge. Let the Gaussian surface is a sphere. Let the Gaussian surface is a sphere which is passing through the point P. Okay, which is passing through the point P, and let the radius of this sphere is smaller. So here we are finding out in the region when R is greater than capital R, that is outside the shell. We are finding out the electric field at a point P which is outside the shell. So outside the shell, R is greater than capital R. Okay, so the same way, let the surface area of this small surface at the point P is ds. So we draw the direction of ds. which is normal to the surface. Due to positive charge, electric field is pointing away. So E and ds both are in the same direction. Let's start from the Gauss law, which states that closed surface integral of E dot ds is equal to the total charge enclosed in this Gaussian surface. Let the charge of the sphere is small q upon the square of the distance. What is the distance? Here it is small r. Okay. E into ds into cos of angle between them. Angle here is 0 degree. Q upon r square. E. What is the integration of ds? ds is the small surface on the spherical surface on this sphere. The integration means the total surface area of the sphere of the Gaussian surface, which will be 4 pi into r square. Okay, the total surface of the Gaussian surface. So radius is small r. 4 pi into r square. Okay, is equal to, sorry, it is equal to q upon epsilon naught. Corrected? Okay, Gauss law states that closed E dot ds is equal to q upon epsilon naught. Okay, so it is equal to q upon epsilon naught. So the electric field is equal to 1 upon 4 pi epsilon naught q by r square. This is the expression of the electric field at a point P outside the shell. Okay, the same expression is for a point charge also. If the whole charge was concentrated at the point O at the center of the sphere, then also at r distance, we get the same expression. So it means that this charge appears to be concentrated at the center of the sphere. So what does it appear? As if the whole charge is concentrated at the center of the sphere. So write down here. Write down the expression is the same. The expression is the same as that for a point charge. As that for a point charge. Okay, expression of electric field is the same as that for a point charge. So it appears as if the whole charge is concentrated, as if the whole charge is concentrated at the center of the sphere. At the center of the sphere. Okay, so the same expression we got for the point charge electric field due to a point charge at small r distances 1 upon 4 pi epsilon naught q by r square, and the same is for the spherical shell outside the shell. So the electric field is the same, that is it appears as if the whole charge on the spherical shell is concentrated at the center. Now let's find out in terms of surface charge density also. We know that sigma is equal to charge per unit surface area. Which area? Area of the spherical shell. Charge is distributed on the spherical shell. Surface charge density is charge upon surface area of which one? Spherical shell. Okay, by charge per unit surface area. Okay, so we can substitute Q is equal to sigma into 4 pi r square in this equation. So what do you get? 1 upon 4 pi cancels off. Okay, 4 pi cancels off, and we get it as sigma into r square upon epsilon naught into small r square. This is in terms of sigma. Here capital R is constant. So what do we observe? Electric field is inversely proportional to r square. Electric field is inversely proportional to r square. That is, as we move away from the spherical shell, the electric field decreases. Okay, now let us find out on the shell. Second case, when r is equal to capital R, that is on the shell. Okay, just substitute small r is equal to capital R, or you can substitute it here also. The electric field on the shell will be equal to sigma upon epsilon naught. Okay, capital R and small r both are equal, so cancels off, or you can put it in this equation also. 1 upon 4 pi epsilon naught q upon capital R square. Now the third case, inside the shell, when r is less than capital R, that is inside the shell. inside the shell. Let us draw the figure once again. This is the spherical shell on which Q charge is uniformly distributed and the radius of this shell is capital R. Now we have to find out at a point Q. So here we draw a Gaussian surface of radius small r. Here I am writing by putting an arrow. This radius is small r. Okay, that is r is less than inside the shell. Again, we start from the Gauss law. Close T dot ds is equal to Q upon epsilon naught. Okay, according to Gauss law, this charge should be enclosed inside the Gaussian surface. Now, this is the Gaussian surface of radius small r. Is there any charge inside the shell? This charge is outside the shell. Q inside the spherical shell. Q inside here is equal to 0. So the electric field inside is equal to 0. So no electric field exists inside the spherical shell. The electric field is only outside the shell. On the shell, it will be maximum. This will be maximum. This value is maximum. And outside it is decreasing. Inside it is equal to 0. So we have drawn the electric field on the spherical shell. We have drawn the charge on the spherical shell and found out the electric field outside the shell, on the shell, and inside the shell. Okay, we can plot a graph of electric field with the distance. Okay, first note it down. Draw this figure. Spherical shell on which Q charge is uniformly distributed. Let the radius of this spherical shell is capital R. First, we are finding out at a point B. So we draw the Gaussian surface, that is a sphere, which is enclosing this charge. Consider one small surface area ds and the electric field. Both are pointing in the same direction. Angle is 0 degree. Okay, now let's plot the graph between E and R. Electric field and the distance. Okay, this is the center of the shell. O point is center of the shell. Then R is equal to capital R. That is, this part is inside the shell. This is on the shell. Okay, and this will be outside the shell. Yes, inside the shell, we have seen that the electric field is 0. Electric field inside the shell, 0 to capital R means it is inside the shell. On the shell, it is maximum, which is sigma upon epsilon naught. And outside the shell, the electric field is inversely proportional to R square, that is, it decreases. So this is the graph between E and R. So draw the graph also. The electric field and the distance R. 0 to capital R, that is inside the shell. Electric field is 0. On the shell, it is maximum, sigma upon epsilon naught. And outside the shell, it is inversely proportional to R square. Okay, so we have completed this chapter. Now you will solve the NCERT exercise questions, also do the solved examples and the exercise questions. Tomorrow we'll be discussing few NCERT exercise questions of this chapter. Okay, so keep studying and write your name in the comment box, especially in this video, in the physics video. You will write your name as I am the class teacher, so I will mark your attendance. Okay, and only 2 days will be given. So from yesterday onwards, you will start writing your name. Yesterday's video also, you will write your name so that I will mark attendance. Before that, you had online or the offline classes and I have already taken the attendance. Okay, so from yesterday, that is 19th onwards, you will start writing your name in the comment box. Okay, after watching the video, keep watching and keep studying. Okay, now tomorrow we'll discuss few NCERT exercise questions of this chapter.